Well, thank you, Hani. I appreciate the opportunity. It's amazing to be with you here. So I want to start this by congratulating you as the latest recipient of I wrote it down so I don't miss the whole thing, the Robert Herman Lifetime Achievement Award in Transportation Science.
Thank you.
I know you were very close to Bob Herman.
Correct.
So what does that award mean to you?
Gosh, yes, indeed, I was close. I was very fortunate, really, to have had the experience I did with Robert Herman, to be kind of his closest sort of collaborator and colleague in the last period of his life, really, not just his active life, but really just his life. That getting that award was it's really a culmination of things for me. This is well, first of all, I wrote the criteria for that award.
Oh, really? Okay.
So I was on the kind of inaugural committee, if you wish, that set up the award for the Transportation Science and Logistics Society, which at the time was the Transportation Science section, so we kind of set up the award, we wrote the criteria, and selected the first recipient, which was Bob Herman at the time. So it is indeed, it's just been a real honor, of course, but kind of, sort of closing of a circle, I guess, in many ways. And so that recognition, to carry an award in his name means a lot. Absolutely.
That's fantastic. We discussed about this. We're going to talk about traffic flow and some history of it and most of it, what you've done in this field. So I looked up your Google Scholar, and you mentioned that before when we were scheduling this. The very first paper I found on it was on dilemma zone estimation.
Correct.
When you were back at MIT.
Yes.
And what was very special to me in that paper, there's a lot of interesting things in it, but something was about data availability and limitations of computation. So one, you have a statement there that this can be done on a calculator. And that was very interesting to me. So, and I want to talk a little bit about how do you think this has played out throughout the years? Not too much data, not too much computation, and moving towards a lot of data and almost unlimited computation power. How that changed things in traffic flow?
It has changed it a lot in some ways, but we still do not have enough data. And getting good data requires a lot of effort. So a lot of the data that we have is not necessarily addressing the questions that we need to address. And so obtaining data is still challenging. And yes, we have more quantities of it whenever we collect it, and it may have more detail. So it requires more effort to process, and it requires more effort to, quote, clean up and so on. And so working with real data is still a demanding task, and it really is still an art, and it's often what differentiates between a good contribution and really one that stands out, I think. And investments in data pay off generally. So I can give you several examples of that, one of which is NGSIM. Okay? NGSIM came as a project, was intended to develop new simulation models, microscopic simulation models. And I was serving in an advisory capacity to the team that was doing this with Federal Highway Administration. And I'm proud that I prevailed on them to invest a good chunk of those funds in collecting data. I told them, collect the data, make it available, and the models will come. And sure enough, for every, you can find so many papers and models and so on that have since been developed using that one data set. I know it has multiple locations and so on, but it was really one sort of data collection effort. And that took a lot of convincing for Federal Highway because their deliverable in their mind, they wanted the models. But there really is no ultimate model because somebody can always improve on that. If you have the data, the scientific community will generally leverage that and translate it into better models. So data remains extremely important. As you know now, also with our TG-SIM effort, for example, where a lot of effort goes into collecting a lot of that third generation simulation, modeling data, and I'm confident, in fact, that it's going to be, again, generating probably, an order of magnitude more work than even NG-SIM generated because it's such a rich data set. And so that's about limitations in data. But computation, I've stated that recently, actually. I'm both when it comes to computation and storage, okay? I always need at least 15% more than what is available for the project that I may be working on. We're always needing more, and it's still constraining for the scale and scope of problems that we, that we work with. And I can go back to that 15%, but I've never, found a bookshelf that I was enough where I couldn't have more room, at least when we were in a physical world. Same on whatever storage resources you might have, and certainly for computing power. And so we can, I think our field keeps sort of leveraging, I think, much of that, of available computational power. And I don't know that the magnitude of new knowledge that we're gaining is, in fact, say, proportional to the computing. It's probably not, it does not scale, it scales sublinearly in many ways in terms of quantity of knowledge that's generated. But certainly the ability to measure makes a huge difference.
So how about the model complexity? So one thing I noticed is it's a lot easier to increase the complexity.
You can, insight diminishes with complexity, unfortunately. And some of the kind of most effective tools and some of the most effective models have been those that translate kind of collective effects in simple relations. And then we've seen that in traffic flow. And that's in part what is nice about this our domain is in that you do have these collective effects that emerge even when you have very complex interactions that are that may be taking place. And so yes, our models increase in complexity, but the insight ultimately comes from more aggregate models or macroscopic type of relations. Though, of course, there's, the microscopic insights are also useful and great, but there you want to look at mechanisms more than what you want to look at. Is it this variable or that variable? Or is it this error structure or that error structure? And we've seen a lot of that kind of trade-off between complexity and insight in the area of travel behavior, where the models have gotten ridiculously complex in many ways, that you have models that kind of fill 2 pages with variables, etc. And then you ask, well, what's the conclusion? And the conclusions usually are either, I would say, obvious, that you didn't really need all the models to sort of conclude that, because you could see it from some of the aggregate relations, or there you just you get lost with so many interacting effects.
There was one paper I found, and I wanted to talk with you about it, which the title of the paper is "Traffic Science: Perspectives on Future Research." And this was very interesting to me because you listed, it's a short paper, it's a 4-page paper, in a 4 pages paper, and you list the topics that you think need to be addressed in the traffic flow community. And so two things that caught my attention. One, was very generous of you. People don't do that anymore that often, at least. People don't share ideas and say how these are the things that are important. And you've done that quite often. And so maybe the latest one that I saw was the one on NFT. But I want to talk about this because some of the things you talked there in that 1985 paper hasn't been done as far as I can say. Still, people haven't found a complete solution. So, and one thing very interesting to me was the effect of geometric factors, like grades and road widths and everything. And so why do you think, some of it has been addressed, but why do you think people didn't look into those aspects? Like geometric seems to be quite important.
Let me give you some background, by the way, on that particular
please.
paper, because that came out actually out of a workshop that was funded by NSF to come up with kind of research priorities, if you wish, in transportation. And that workshop was held at Northwestern. And the person who organized it was David Boyce, Professor David Boyce, whom you know, of course, who at the time actually was not at Northwestern, but he organized it at Northwestern because it had, the setup and so on. And that workshop had a section that dealt with demand, one that dealt with traffic, one that dealt more with like routing and supply and logistics. So it kind of covered different areas. And each area had a kind of a state-of-the-art paper that was commissioned. That's and that special issue, I think, of transportation research, and then discussion papers. And so I wrote that as a discussion paper to kind of fill in the blanks that I thought were sort of missing in the commissioned paper, the state-of-the-art paper, because I felt those were important questions. And I was kind of a very junior assistant professor in those days. And I thought that having them in there would in some way impact like what NSF would do. So I thought I was kind of helping NSF identify research priorities. And I thought it was really important to contribute something in there. But of course, now we know that these are, they go to the community, help identify things. They have no direct implications on funding. But in those days, I thought it might. And in fact, it's interesting because NSF used to not really fund anything in transportation when I started out. And that workshop was part of so the transportation community tried to put some pressure on NSF to recognize transportation as an area where they should fund things. Before, mostly the civil and systems group was funding structures and mechanics, and so a more traditional civil. They did not think transportation, there weren't that many funds anyway for civil. They didn't want to kind of split it further, share it with other communities. And they felt that the U.S. Department of Transportation is the one that should be kind of funding transportation. And in their view, there was, DOT and the state DOTs were funding research in transportation. So why did we need NSF? And the case that we were making is there are all these fundamental questions in transportation that need to be done so that agencies can then fund the application of these tools. And that workshop was one kind of activity. And so NSF funded that workshop, and they did fund a few projects. And in fact, I was fortunate to win one of those because that was such an important, first award for me from NSF that allowed me to start the work on the dynamics of usage decisions in transportation systems, on which I built quite a bit of work subsequently because we were, and that it was integrating kind of user choices in a traffic system and a network ultimately. So that was a very important award for me. Anyway, to go back to to your question, which I have not answered yet, on why we have not seen much of that research with geometrics and so on, it goes back to how research communities evolve ultimately. Those who are concerned with the effect of geometrics had been the highway engineers, the highway designers. And at the time I started my career, there was really very little new highways, sort of very little geometric design being done. I mean, it was fairly standardized, and all the AASHTO manuals existed and were developed. The heyday of that research was in the late 60s, actually, where people were looking at the impact of length of ramps and merging areas and things like that, where the geometrics were really studied. But beyond that, there was very little being done because, in fact, the data was not quite there. So the main source of data was loop detectors. And unless you invest the effort to go and do video imaging, which in those days you would have had to pretty much analyze manually, because you didn't have all the image recognition software, etc. And so that, I think, the lack of data availability, but also nobody was asking the questions anymore. But those continue to be factors. I mean, I've tried later on to work on the effect of grade, for example, which is extremely important and is one of the reasons why we find flow breakdown occurring in actual traffic systems. And people now recognize it, but you will find very little sort of formal scientific research that is addressing that. And part of what we've seen also, again, is kind of a separation between the engineers on one hand and the scientists on the other, which is really unfortunate and something that I have tried to address, throughout my career. In fact, trying to kind of, bridge the gap to the extent possible.
You mentioned something interesting about the funding.
Yes,
I noticed in earlier in your career, the funding sources were completely different. Most of them don't exist anymore, replaced by other things. So you had quite a bit of funding from like General Motors, which had an office which does not exist anymore.
True. Well, that was not very common funding. That was rare. Okay. And that was, I'm going to say, relationship funding, in the sense that, Bob Herman, Richard Rothery had connections still with people who were there. And as the GM labs were phasing out of traffic research, they kind of went to researchers to look at some questions that were of interest. Intelligent transportation systems movement was beginning, and GM was kind of looking for what its role might be in that work anymore, or traffic science anymore. Yeah. And so that, they thought there was value. Could fund something if one has the sort of, the right topic for them or the right connection. But sure, by and large, they did not, the willingness to fund that kind of work diminished. In fact, it diminished way back, and that may have been one of the reasons that Robert Herman and these folks kind of moved out of there. The way the labs survived is ultimately somebody who was in their traffic or transportation research labs was able to convince the production folks that logistics was important. And so they started doing logistics work that was feeding directly their logistics and manufacturing processes. And that's what kind of kept it alive, because, again, within corporations, priorities shift. When you're not, the profits diminish, some things have to go. And unfortunately, they just decimated the entire group and capability that pretty much kind of gave traffic science the main sort of the big push and the big jump to sort of become an established field. I mean, if it had not been for GM Research Labs, we would not have had the field of traffic science, because they invested, again, that was when Bob Herman was there and was leading it. They kind of just built the entire foundation of this field. They invested in vehicles and drivers to go collect data. They did experiments and so on. And that's really what built the foundation.
So I want to move to a different topic. And so in 1984, you published a paper on the network level traffic flow relationship.
Yes.
And I know in that paper you thoroughly investigate the application of two fluid models. I know, like Bob Herman published before that. So, and you have multiple papers on the topic after that. So, and so I wasn't aware of this. It's for someone like me who came in in 2010 or something around that. So we saw the new wave of network level traffic flow. So I want to get your opinion on it. So what initiated that research? Why was that? Why did you do that, and how it evolved during that time?
So yeah, that's a very interesting question. Actually, it tells you that things happen kind of surreptitiously in many ways. So when I graduated and moved to Texas as an assistant professor, and by the way, I was hired because of that Amber Light paper that you mentioned earlier, because that was published in Transportation Science, and Bob Herman had seen it there, and so he was, interested, I guess, in talking to me at the time. And then I interviewed, etc. But so when I went to Texas, Herman was working on the two fluid theory of traffic flow, which was envisioned as a theory of urban traffic. And by then he only wanted simple sort of relations that translate collective effects. And that theory he had developed with Ilya Prigozhin, who was the late Ilya Prigozhin, who was a Nobel Prize winner in chemistry, in thermodynamics. So he had done. So he and Prigozhin had initially developed the kinetic theory of traffic flow, and I understand that monograph, that book, was written in pretty much in 1 or 2 weeks when Prigozhin was visiting Herman at the GM labs. So anyway, a few years later, they came up with this two fluid model, and the two fluid model is a very compelling logic to it, because it views traffic in an urban network as either or stopped at any given time. He was very much invested in that, and he had come up with this relatively simple way to collect data, and somebody is recording that with you. So you have a driver who is kind of a particle that's sampling the traffic, because you're told to just follow the leader and do it for a certain duration, and then follow another car and another car. So sample many particles in that network. It's only two of them. That kind of relates how pretty much how the stopping time increases as the fraction of vehicles stop. And so he had been working on that. He had a PhD student named Siamak Ardekani, who did his PhD on that particular topic, and most of their work had been collecting data by driving pretty much in these cities, but never quite fully exploring the full network. And with my interest and my sort of skills, I guess, I thought it might be interesting to see what happens in a full network. And the only way to do that was to then microsimulate. at the time was NetSim. And NetSim was available, though from my earlier work, I had source code for NetSim. Somebody at Federal Highway had sent it to me. And so we were able to do some modification. A student there who was a PhD student named Jim Williams. And Jim Williams had worked as an engineer at Texas. The experience with how you time signals and so on. And so he went into NetSim and created some of these network scenarios. And what we were doing in a micro-simulated system. And our first thing when he did that, after we had set things up, and of course he had to do different, let's say, from we're not estimating. It's just the micro rules of car following, lane changing, stopping at lights, lane discharge, etc. So we thought it'd be interesting to see what emerged. Fluid model did not, quote, validate. We didn't see that. And so Jim and I were looking at this like, how can we tell? I said, no, we have to really look at this closely. And so we started looking closely at it, and I told him, Jim, how are you getting stop time? He said, well, the default stopped. I told him, no. The fluid model stopped as stopped. It has to be 0. So he went in because we had source code, and he changed that and to be actually 0. And sure enough, he ran it. Everything fit perfectly. So that was a kind of a first interesting revelation when using off-the-shelf tools. This the definition of the variables. So that's how we got into that. And then as we were simulating these, I was really interested in seeing what might be the network level relations. And the key question, and why we do give credit to some early UK researchers that had looked at some aggregate network level models. Nobody had examined fundamental diagram with these variables. That was completely, that was the first time. And so we then had to define what might be a network level flow, what might be network level density, etc. And density was relatively easy to define, of course, but when it came to flow and how we get the speeds and so on, that was problematic, mostly because we also had the information the summaries that we had were in NetSim, they were link level. So we had to define a link level average flow and so on. And so they were basically weighted averages that were created that way. Sure enough, that's where we then developed the network level fundamental diagram. Green shields or green shield-like models and relations, and the flow density relation, the fundamental diagram, and that we were just super pleased to find that, sure enough, the theory applied to networks or the collective effects produce similar relations in networks, and so on. But mostly that's when it kind of emerged through simulation because we asked that question of the tool. We did not have trajectories that were coming out of there, and it wasn't until much later in work that we were doing with realized that we could adapt Edie's definitions of the average density, average flow, and so on. That topic. And so Jim Williams did his dissertation on that. So we had several papers and publications because of the examined many answered all that could be answered, at least through simulation, or the level of simulation that we had, until we then got into DTA work, a dynamic traffic assignment. We were doing simulation assignment, validating the simulation by the fundamental diagrams it was producing. And it was so dynamically, like over where the flows are time dependent. So from a single run, you build diagram. With NetSim, we were doing steady state runs pretty much because that's all it would allow you to do. NetSim would not that it had reached steady state, and then it starts collecting information. So each value that we had, let's say, of density, and so whereas with the DTA work, we started looking at it being time dependent, and in work that we did with Srinivas Pita in the 90s, really, we found a hysteresis pattern just as we have on individual links that was forming at the network level as well. So that, we visited that, but truth is, nobody was paying attention to that work. I mean, some people early on because we published the network fundamental diagram in ISTTT, go very far. And truth is, we didn't use measurements. It was based on simulation. And it really was not until, so there were some measurements that were done by Herman and Ardekani, and they were, they used at the time aerial photography but they could only get like one data point from that. You couldn't really do a fundamental diagram because you're circulating. There's really just one density value that you're going to get. So they could not explore that sufficiently. And the other work that Williams did, he connected the two fluid model to the fundamental diagram by essentially postulating a relation between density and fraction of vehicles stopped in the network. And so that connected then the two fluid model and the fundamental diagram, and then you could have all of those relations. I'm still waiting for someone to pick up on that, frankly, because it hasn't happened. On the other hand, the one entity that did notice, the Traffic Flow Theory Committee at TRB, is where we had sort of presented several of those results. And in fact, Nathan Gartner noticed that, who he was chair of that committee. And when we did the follow-on to the traffic flow theory monograph, he wanted a chapter there on macroscopic relations at the network level. Unfortunately, they called that chapter they called it a macroscopic, or it was called macroscopic traffic models. Our colleagues called it macroscopic fundamental diagram, which of course is confusing because all fundamental diagrams are macroscopic. And so the correct terminology to differentiate, to really refer to it as a network level fundamental diagram. Subsequently, the work that Professor Carlos Daganzo and his student at the time, Nicolas Gerolminis, kind of essentially validated the network level fundamental diagram using actually Yokohama and other places, and kind of derived it for pretty much for steady state conditions. Or rather, derived it more as a steady state or equilibrium relation, which is what the fundamental diagram is for links ultimately. And so that really gave it a huge boost in terms of of course, that work got a lot more citations than our original work. That I would say that the community has been generous in recognizing the earlier work that we had done with Bob Herman. Pleased for that.
So there's no follow-up model on the two fluid one.
Some of Herman's students did some further work. There were some applications that were built. For example, Elizabeth Jones at the University of Nebraska at Omaha at the time did some work on that with students, mostly calibrating it based on driving. Examine further aspects of the two-fluid model. But unfortunately, there has not been any sort of major sort of breakthrough, I guess, that is related to it. Other than, that's been connected further to models of travel time reliability. But that's, again, has not been hasn't gotten much traction, I would say.
I'm just looking at it. You can get satellite images, and you can get them very frequently. You can do all those measurements significantly easier.
Absolutely, yeah. I think one definitely could look at that again with real data, and especially with helicopter data collection. I remember when back when Herman and Ardekani commissioned aerial photography, they had to analyze the images using photogrammetry. I don't know if you remember that. Probably not, because it was, it didn't exist. We're not using that anymore. But this is one where you put images together, and you have to look through like a stereoscope, so you can so you could see the image, and that's what they were using to analyze those images. Very, very time consuming.
I've seen a lot of recent work, maybe not a lot, but a few recent work on it. So a few years ago, patterns. And recently I saw a few papers coming from Marta Gonzalez, Jorge Laval, and Monica Menendez on percolation and how that how congestion essentially propagates in a network.
Yes.
And so the critical percolation point where you call something congested versus you call it uncongested. And so I don't know, do you see any connection between the two?
There's always kind of a judgment call ultimately, and I think where you said the thresholds matter. I'm not really prepared to elaborate, I guess, on that question right now.
That's okay. So this is more of me being curious.
Yeah. I will say that we haven't always been consistent in defining congestion points. So that's and ultimately how you set those thresholds may. It's the same when you're looking at flow breakdown, for example. How do you define it? You need to generally do sensitivity to the various measures that you're using. for that, but one can use more precision ultimately for these definitions, but I don't know that I still think they're going to be sort of site specific ultimately in terms of how you would set them.
So I want to continue on the topic of simulation.
Okay.
So, and you've had a huge impact on this field from simulation perspective. A lot of it related to mesoscopic simulation, which I don't want to talk about. That takes a whole day to talk about. So, but I want to start with pedestrians.
Yes.
So, in early 1990s, you did this huge project of simulating Hajj and part of it. And so there's some very interesting thing that you introduced in that paper, which was very interesting to me, including the radial formation of the cells. So what was the story behind that, and what was the how did you get to a point that, okay, the traditional models won't solve this, we need something new?
Really, that was one of the very first, that work that we did with Saad Al-Ghadi, who was a student from Saudi Arabia, who actually came to me saying, I want to work on crowds at Hajj. I'd never worked on pedestrians before. So when I said, yeah, that sounds really interesting, fascinating. Where are you going to get data? So he actually went and got data. He went one summer during Hajj, and he collected data, mostly with video images, which he then brought back, and we hired undergraduates, and they were counting the pedestrians in each of the cells. So, and the system he was interested in was the jamarat, which at the time consisted of circles that pilgrims approach, and then they throw pebbles, 7 pebbles. There is kind of a column in the middle that most of the pilgrims wanted to hit. And at that time, that was one of the areas where there were the most accidents, where there would be stampedes, there would be various issues going on. And so that was the model, the system he focused on. And so since that was a circle, it made sense to then, have kind of a circular radial definition of the cells. And we developed it as a cell model because that's how we were modeling traffic, in fact, macro or mesoscopically. So that was that was a meso model ultimately, because we were using macroscopic relations, and that's the first model that we had done. And but we had microscopic elements. We still had all the particles in there that we were moving, and we had elements where they were like throwing the pebbles and the distance they were using before they would start going back. And the key thing there was the interaction between those who were approaching the edge to throw their pebble and those who were leaving. So it was multi-directional, both inbound and outbound, as well as circumferentially in there. And like I said, he had collected data, calibrated all these relations, but that was that initial model was a macro-meso type model with some microscopic elements in it. Later on, we did a model of Hajj, and that was with Ahmed Abdul Ghani and Khalid Abdul Ghani, twin PhD students who worked with me at the time. And we did that when Saad Al-Ghadi was visiting us at Texas. And so we built this model of tawaf around the Kaaba, which also was it's a circumambulation where you go around the Kaaba. It wasn't a full circle necessarily because the geometry was not perfectly circular, because one area was larger than the other, so you had asymmetries in the formation. But that one we built as fully agent-based, cell-based. So the movements from the cell were individually based on various rules having to do with really more the directionality of the pedestrian. And that simulation framework then was much broader because we've applied it to other situations other than just the tawaf situation, whereby each particle then has a destination. And that destination, they have a route that they're trying to get to as directly as possible. But then, given the obstacles, they will try to essentially get around it in a very local way. And that's how the transmission sort of takes place. And that was fully microscopic. And it was essentially an agent-based cell model that governed the movement of these pedestrians. And for that one, initially, we really did not, we kind of had data that was more macroscopic because nobody was collecting data or analyzing it anyway. So the macroscopic data was more how long does it take? And so there are statistics on how long people took to do that. Later, we convinced the Hajj sort of Research Institute to use trackers on pedestrians to start collecting some data. And then later on, they invested a lot more in collecting video imaging and so on. And I had a very long engagement. Subsequently, just as the evaluate different designs using the simulation tool that we had developed with Abdul Ghani, Ahmad and Khalid.
So by the time you were doing this the second time, the pedestrian models was significantly expanded compared to the first time, right?
Correct.
So it was like social force model existed at a time. So what was the decision factors that you chose this approach versus other ones?
It's what worked ultimately, and it's one that gave us a lot of flexibility. Ultimately, a lot of flexibility in configuring the space, a lot of flexibility in terms of testing various designs and so on. And so I think that's in large part why we use that approach. It's just the flexibility that it provided, and it did not require sort of it wasn't locked into calibrated parameters in the same way. The main kind of function in there was a kind of a crowdedness tolerance function, okay, that is distributed across individuals. Some people, so as the crowdedness increases in a certain cell, your tolerance for it decreases. So fewer people are willing to jump into a crowded space, whereas if it's open, the likelihood of jumping in there is going to be much higher. And so that was one of the factors that impacted that behavior. And you could then kind of, do sensitivity on some of these parameters and have folks who are, again, congestion averse or crowd averse versus crowd seeking, if you wish. But and then it becomes kind of a sort of like a local path choice problem in terms of how you get there. So it gave us a lot of flexibility. It seemed to work, and it was more readily computable than models that were embedded in some of. By then, there were commercial tools. At the time we started the work, there were no commercial tools. But by the time those commercial tools were available, computationally, they were just so demanding because of a lot of the. They were pretty much. They considered. The individual level calculations they were doing were just very, very demanding, and you kind of needed to evaluate scenarios a little faster and for a longer period of time. And I was very interested subsequently in looking at just the whole build-up process, the fill, and then you operate at steady state, and then the whole kind of process of, is this continuing to fill up, which is a problem at a certain rate, because you need to really manage the space because you can easily reach gridlock in these kind of systems.
Let me go back to the traffic vehicle side, to
Yes.
car following and chain models, and that this can take a long time, but I want to focus on a specific issue. So maybe One way of approaching this maybe is to combine this with generally ITS work. So you were there when ITS started in some sense.
Correct.
It has had many different names over the years.
Correct.
But what was the motivation and what caused that movement? Say we need something like ITS. Let's start looking into it.
Well, these were really different sources of push, I would say, of technology being sort of pushed onto the system, and factors that were sort of pulling into this particular system. One was that the technologies were becoming more readily available. Technology, that is the information communication technologies, were beginning to spread in different domains, and traffic management seemed to be one that where it made sense to deploy it. So there were companies that viewed this as being a new market for them, and so they were kind of going in that direction. There had been advocates within the U.S. Department of Transportation for automation, and that goes sort of way back. And there, the motivation was both safety and flow and efficiency. So there was a recognition that as you automate, you are going to have better safety and better flow. So there was a group that was sort of receptive to that. There was a recognition that that field had not really seen much development since the early 70s. Really, everything that was being deployed was kind of existing. The signals were, traffic signals had stabilized technology-wise. We were not really seeing very much that was new. You had freeway congestion with very little to sort of manage it. People had given up on managing freeways other than some ramp metering that had been done before that. So there was a receptive application domain. There was an industry push, and there was another government policy push at the time, which is that happened to be the time where a lot of the nuclear sort of labs, etc., nuclear research was being decommissioned, as there was detente between the U.S., the East and West blocks, basically. And so people were trying to think of what might be kind of good civilian applications, and intelligent transportation systems seemed to be a good place to employ, physicists, etc., who were looking for something new to do. So some of the national labs got into the act as well. So all these things kind of merged together and sort of helped push that forward. And it was an international movement, not just here, because you had Japan, you had Germany, and the U.S. were the main areas that were advancing that. Germany, because it had the auto industry, of course, and the traffic control industry was there. Japan, because they had essentially their police entities that managed their freeways needed some to make them safer, etc. And then, of course, the U.S. for the reason that we mentioned.
That's interesting. So one thing I noticed was that the role of understanding of human behavior and the response of human to information was recognized from the very beginning. You have a paper on it, but as I look into like the history of this,
yes,
we still don't really fully understand this. Maybe part of it is because it's changing, but do you see that as a huge factor that is delaying the progress of ITS? Or
well, I think you mean human behavior.
Yeah, human behavior, or
I think we have enough understanding of human behavior to manage the systems and to have managed the system. I think ITS, in my view, was a big missed opportunity. I was personally much more optimistic about what we could achieve with ITS, and I've given several presentations where I kind of lay out the vision and where we are and what was accomplished. So it did raise awareness of traffic management. It introduced a lot of sensors. So we have sensors, but in terms of interventions, it has been very disappointing. The agencies have not gone far enough in acting with the information. So you say we can see what's happening in the system, we can display it. Well, we can do some prediction, limited prediction, but that control action, the management actions, agencies have backed off from. On the, at least, on the public sector side. And so that remains the case today. And that's one of my concerns, frankly, with autonomous and connected vehicles, because as you know, the connected vehicles concept has been around for a long time, but we haven't seen much of a deployment of that. Other than what the OEMs are now providing. So the OEMs are giving us connected vehicles that are serving the user, but not necessarily serving the system. Similarly, OEMs are giving us and will be giving us a lot more autonomous vehicles with many automated capabilities. They will serve the user, possibly safety, etc. How they impact the system. There's still a lot of apprehension about that. And this has been the story, I think, of traffic management and transportation system management, for as long as I can remember. Back to human behavior, that we do know a lot about human behavior, at least for those practical situations where that behavior is important. We know a lot about the areas where it fails, that it has impact for traffic safety, for instance, and that's where developments in autonomous capabilities and so on tend to, or have the promise of overcoming some of these limitations, that we may not necessarily be able to predict the exact route that somebody may choose. We may not be able to predict, the exact route that somebody is following. May not be as critical to our ability to evaluate different strategies, because if you recognize heterogeneity across users, ultimately, you're bound to hit it in distribution, to sort of get something that is reasonable in distribution. Even though you may not for individual eye be able to predict exactly what that individual will do, when you look at it in distribution and you have heterogeneity in the system, you're going to, on average, be able to examine what the properties of that system might be. So we've learned a lot. Also, a lot of what we've known, though, has been in different domains and has not been fully connected. And that's been one of my sort of concerns, I guess, in my own research, to try and connect what is considered travel behavior versus what is considered operational decisions, let's say, in traffic flow. And those have been different communities. We have at least been able to get some of the tools from modeling choice into microscopic traffic models. We've made them as complicated as the travel behavior models in some cases, but it's not clear that they produce, they do produce refined phenomena, better. And so when Samer Hamdar, in his dissertation, introduced heterogeneity in car following, you could then see the scatter that was reproduced, that we typically see in fundamental diagrams, was being then reproduced in the simulations that were using that model. So I think that is, an important refinement in the modeling. And so there's, areas where we can do better in capturing human behavior, but recognizing heterogeneity is probably the most important factor or aspect in this work.
So yes, you've had multiple very influential papers on that area, right? From Samer, and then with Jiwon Kim, you had
and Talibpour as well. Yes,
and the correlated parameters.
Mm-hmm. Yes.
It was a huge. I think that was the very first time that concept was introduced, right?
Yeah, surprisingly.
Yeah. So let me let's talk a little bit about the connecting and automation.
Mm-hmm.
So we did.
Yes, we
give
did.
credit to myself a little bit here, but really you did that. So looked into how connecting and automation can change the perspective in the system,
Yes.
at the link level and at the network level. And since then, there's been a lot of studies on that area. And you also mentioned that there's a disconnect between who's building these technologies and who is supposed to utilize them. And so where is this going in your opinion? So is there going to be a convergence point between the two, or should there be a change from a traffic flow perspective to recognize that there won't ever be convergence? Let's use that as assume that exists and just move, try to improve the system with what we cannot access.
It's difficult to predict exactly how that will evolve, but the indications in the short term are that these are going to be vehicle features, essentially, and that they are going to be in some way accepted, integrated, regulated into the traffic stream. How we then utilize these very capable particles to improve flow, the kind of things that you studied in the various projects, things like trying to predict the occurrence of shock waves, for instance, and then avoiding them and so on. It is not clear who is implementing or deploying. I think federal research here is recognizing these capabilities, but federal level researchers do not implement directly. In the US, at least, it is states that implement. And so they kind of need to then have states on board to do implementations of some of these things, because the federal government doesn't really run any intersections directly or any highways directly. And that becomes then a sort of a political process or a policy-oriented issue. But on the other hand, both state level and federal are recognizing that this could in fact be a game changer. And they're kind of treading a thin line between encouraging the deployment and testing and so on, and at the same time kind of regulating, not crossing a certain line. And we see a lot of difference now when you look at states and communities and so on. I think there were cities who wanted to ban. I think Chicago was one of them, where some aldermen wanted to ban autonomous vehicle altogether from Chicago streets. And I just think how regressive such a move would be in terms of the technological role that a city like Chicago might be playing to industry, in fact, where you have automotive related type industries, for instance, that would be that need to be testing some of these vehicles and what have you. So we're there, and I don't know what the solution is to these issues, frankly. I do know that they will continue to be deployment. Where I view my role as a researcher is to understand the interactions. Understand how these individual vehicles behave. How do they interact with the rest of traffic? Is that interaction safe, essentially? And what kind of impacts would it have on the traffic stream? Everything seems to indicate that the impacts are overwhelmingly positive rather than being negative. And so as more evidence of that is available, it will probably, hopefully, allay the concerns that some might have in terms of further deployment. And it may then encourage agencies to manage traffic, recognizing the potential of these vehicles, not only to protect against what they might do negatively. Unfortunately, along the way, that every time something goes wrong with an autonomous vehicle, it's like the whole industry and the whole program is then being questioned. And that's truly unfortunate in a way, because one has to understand, why did this occur? Is it likely to occur again? Is this something that can be corrected? And in most situations, something that that has been corrected.
So, for a long time, from traffic flow perspective, the source of heterogeneity is humans. So you had just one type of car, maybe you could have trucks and passenger cars. And then the human was the source of different behaviors. And now it's not just the humans, we also have the technology involved as a source
Correct.
of behavior. Do you see that? And now we have a lot of new models that are targeting not just human behavior anymore, but also targeting the vehicle. And so, how's that changing the landscape of traffic flow research?
Well, you mentioned that humans are not the only source of heterogeneity, because vehicles, a Corolla, in terms of capabilities, acceleration, deceleration, and so on. So all of these things that tend to magnify the heterogeneity in humans are also very important to recognize. Not just trucks, let's say, and cars, but within vehicles, that makes a huge difference, particularly when we go back to the geometric effects. If you have grades, you have an underpowered car that is definitely going to create a shock wave compared to one that can actually accelerate, for instance. And so now with autonomous vehicles, I think that the variability is in fact reduced, not increased. Even though you have different OEMs with different logics, that is still going to be less variability than exists across humans altogether. And particularly when it comes to the extremes, because what causes the problems are the extremes in human behavior. Either there's inattention, and so there's slacking, or there's aggressiveness, where you are overreacting to situations. And autonomous vehicle logic tends to not do that. And as you know, in the preliminary data analysis we've done in existing deployments suggests that there is much less variability in things like acceleration, for instance, when you look at autonomous versus human drivers. And I expect that to remain the case. And so heterogeneity is in fact decreased. And because of that, we can achieve closer following distances. We can achieve more reliability and stability in the traffic stream itself.
Do you think that the relationships like two fluid models would still stand if you have a good proportion of autonomous vehicles on the road?
Yeah, I think two fluid will still stand, and fundamental diagrams still stand. It's that the parameters are changing. The key issue is, as you know, to me, understanding sort of flow properties based on microscopics goes back to the very simple models that the GM labs had developed, that Herman, Rothery, Gazis, those scientists had developed at the time. And there's two parameters mostly in these follow the leader or car following models. One is the reaction time. The other is the sensitivity of the reaction. And with those two, you can very much intuit or understand the stability, because we know that the longer the reaction time, the less stable traffic is going to be. And the extent of the sensitivity can either magnify or reduce essentially what the impact of, say, waiting too long, for instance. And so, but reaction times in particular, as you reduce those, then you don't have to accelerate as dramatically or decelerate as dramatically. So that's where you avoid a lot of the causes of shock waves. And as we've seen in simulation models, road experiments, and so on. And so those, I always go back to those two parameters to try and explain what happens, because we know it's the product of those two that effectively determines whether you're in kind of what kind of stability regime you're in.
So does that mean that, and you've done a lot of work on predicting the breakdown with Jingdong and
Yes.
travel time reliability. Do you think this would result in a more predictable behavior around the breakdown point and near the breakdown point after the breakdown happens?
Well, very, very much so. In fact, I think we can mitigate, we can, first of all, prevent a lot of breakdown instances, because breakdown occurs when shock waves are sort of propagating and expanding. And so that, we can essentially go to situations where the platoons become string stable or asymptotically stable, as opposed to propagating that disturbance further. Now there will always be disruptions, disturbances. It's really how you deal with them ultimately that makes a difference, even whether you can absorb them or not. And I think the likelihood of being able to absorb those increases significantly when you have autonomous logic, and similarly, so you could avoid, you could extend the time before the onset of breakdown, and you can mitigate it once it occurs and potentially be able to reverse it more quickly.
So
and so that might affect, in fact, what happens at the hysteresis point, and avoid that. And simulation results at least suggest as much, that you can certainly, if you look at fundamental diagram, you can push that point of instability significantly and then retain much more throughput in a stable way that otherwise would have been unstable with human-driven vehicles.
So that whole idea of three-phase fundamental diagram, that synchronized flow is essentially disappearing in some sense, or
well, I know, since synchronized flow can become more stable, I think it can definitely, in fact, anything can exist even more so, because synchronized flow is vehicles that are kind of moving fast, maintaining their speed, but at fairly high density. That tends to be not very stable. And so you can increase the stability of that up to a point, depending on how much merging, lane changing is going to be required. Create these perturbances that we should be able to absorb a little better, but then you could think of the need of changing lanes can be anticipated further upstream and take place when it is less disruptive, which humans may not necessarily do.
This is sort of a step back. So,
yes.
So when I was looking at the early work that you did in both traffic flow and dynamic traffic assignment, there's a very close connection between them, and a lot of simulations are fairly
yes.
simple. And when I look at the work that's being done now, it feels like these two fields are fairly separated from each other. Do you feel that, or you still think these two are very much integrated?
I think they're closely aligned. I think the communities in part are separated, but they also overlap in some instances. And that's been, a lot of our work and work that my students have done and so on have kind of kept the two together. But there are then aspects that are kind of more purely traffic flow that do not necessarily need to carry over to the DTA world. And similarly, there are algorithmic questions on the DTA side, particularly having to do with solving for equilibria and fixed points and so on, that do not necessarily call on the sort of the traffic microscopics, if you wish, or on the physics that you're using in your representation. That's how I kind of like to think of it. You have these network assignment problems, but the physics of representing traffic can vary. They can go from the microscopic to the mesoscopic to macroscopic to anything in between, basically, and you still have some of the same issues from a network computation, again, solving for fixed points, etc., that are going to be independent of traffic physics, or or would be rather applicable with a variety of traffic physics that you may be using there. So there is some separation, but to be able to be effective at the work you're doing in dynamic traffic assignment, you need to understand the flow properties, because the first wave of dynamic traffic assignment that was not simulation based was all incorrect, basically, because they failed to understand some very fundamental properties of traffic flow.
So I want to talk about a little bit about AI.
Yes.
And what I noticed was you were one of the very first people that used the terminology in your research. So you have a paper in 1990s that you're using AI techniques. And then, so in recent years, it's significantly influenced traffic flow, and it's changing the way we're looking at things. And a lot of me being one of those people are guilty of this, replacing some of the models that are simple and effective with significantly more complex models that are equally effective in many cases. So what's your take on this? Where do you see the impact of AI on traffic flow?
Well, I was really not one of the first to use AI. There was a whole wave of AI in the 80s. That's the expert systems wave and so on. And in fact, I taught a class back then on AI methods in transportation, where I taught them how to build knowledge-based systems using tools that existed for that. And I even taught them Lisp. I taught myself Lisp, and I taught it. And one of the key things that I learned there was the A-star algorithm, which was used for pathfinding, but it was developed by computer scientists. I did have a couple of students at the time, we're talking sort of late 80s, who really saw that as an opportunity, and they then took a whole set of courses in computer science that was like the AI sequence. Okay? And so that was an area where things were growing. Where we applied it at the time was for design. We applied it to transit network design, which is an area where you kind of have a lot of heuristics being used, a lot of human knowledge. And we wanted to kind of try to integrate that within formal algorithms. And they were actually heuristics that were developed that kind of incorporated both kind of the knowledge side and the more formal sort of algorithmic elements. And it was, I would call it more, it was AI inspired, but more by the desire to incorporate sort of human designer heuristics within a formal systematic methodology. Okay, but somehow that ended up being a wave, a fad that did not fundamentally change things, I guess, in transportation, and ultimately even in AI. I mean, in computer science, all the startups went bankrupt, did not stay in business, and a lot of the investments went nowhere, etc. And so later, of course, so the other thing that did, of course, remain there were neural networks. So neural networks continued to be developed. Then we got into deep learning and so on. And a lot of it is really Google. And I think Google is sort of, at least as I understand it, was where AI continued to thrive and develop and find applications, etc., and to where it then re-emerged with a variety of tools that were available for other disciplines to then use. And so where it has reappeared within the traffic flow world is in prediction and trying to predict short term, for example. But and so all prediction areas where you could show generally better results with AI tools than conventional models, because AI tools essentially have more parameters. You're more parameterized. What is not yet established, and that continues to concern me, is it does not mean that you're capturing sort of structural relations. So when you have disruptions, that very well-trained model is going to get stuck. And that's where I've kind of advocated we need sort of hybrid tools where you do have a structural representation of traffic processes combined with what neural networks and other AI tools could give you, so that and some have called them physics-inspired AI. Okay, and I think that's what probably appropriate for us. But if you put one of our more sort of traffic-based prediction tools against multiple layers of neural networks, the neural networks are going to do better for most stationary processes, or most processes that do not depart very much from observed conditions in the past. But should you have a crash somewhere and the road being not available, or a bridge that disappears, what have you, then the ability of these very well-trained models is going to be fairly limited. And so I'm very open-minded to tools, new tools, and so on. I don't believe in dogma when it comes to methods. I'm more interested in solving the problem and understanding the phenomena there, and representing those phenomena, rather than kind of adhering to a particular rigid sort of school of thought. And so, yeah, we'll as long as my students are willing to go learn these tools, I'm perfectly up for testing them. But I'd like to be able to sort of test, to essentially validate and understand the realm within which these are going to be applicable or not, and what might be a sort of a meta model, if you wish, that's going to be applicable in a variety of situations, and we'll be smart enough to switch gears as needed.
So, a sort of related topic, and that goes to the transportation journals. Like,
Yes.
you talk about transportation science, and
Yes.
science has been, for a long time, was the best journal, the most respected journal in our community for
Yes.
a long time, and so
It still is.
Still is, yeah.
Yes.
And then a lot of other journals are catching up. Just a lot of it is because the new thing like AI that are being developed, and it doesn't necessarily fit within the boundaries of transportation science publications. So, and I want to ask you about how do you think the future of that journal, since you've been very close to that particular journal for a long time.
Well, here's the thing. So the more prestigious a journal is, the more risk averse it becomes, and the more critical its reviewers become. Now, the same reviewers may be reviewing for another journal. When they review for transportation science, they were going to have something, but is this good enough for transportation science? And this is not really the criterion here. Ultimately, is you want to evaluate the work. And part of the kind of challenge has been to introduce new ideas and in that journal. So take kind of one thing ITS did, for instance, is it brought in a whole new field to us from control theory. And there's a different tradition in control theory than there is in, say, network optimization, or more generally in vehicle routing, which are fields where you have formulations that are clean with well-established mathematical properties that you could solve, at least in small sizes, exactly, and so on, generally for static conditions or predetermined time varying conditions, where you know a priori what the time variation is, versus situations where you're relying on real-time data to make decisions under uncertainty and so on. And those papers were struggling with in transportation science because you cannot prove the properties of the model. What is an exact solution? How is the benchmark? What algorithm, what theorems can you prove about it, and so on. And I when I was editor-in-chief, I tried to bring back some of the better quality work in that area. And I know Karen Smilowitz, now the current editor, is also trying to open it up a little bit to sort of new ideas. One other way to open it up a little bit is to have invited articles occasionally. And so for the 50th anniversary, for instance, the editor at the time, invited several contributions, including one in the area of operations, which was on connected and autonomous vehicles. And so that's one way of helping seed new areas in the journal, because otherwise the reviewers were always going to say, well, we're not exactly sure. When in doubt, in a prestigious journal, you reject. And in fact, the Transportation Research Part C was established and founded, because I was one of the founding editors of that journal, largely because all the work that relates to ITS needed a home. Ultimately, it was very good quality work, but it did not adhere to the same specifications of the more traditional work in, let's say, network assignment, or static network assignment, or the work that transportation science was increasingly featuring. And in fact, transportation science saw a reduction of traffic flow work, because, truth is, the field for a while was very stagnant. And it was stagnant because in the early 70s, the US Department of Transportation decided that we know everything we need to know about traffic. Now we're going to concentrate only on applications and tools with the existing knowledge that we had. And that was unfortunately rather short-sighted, because that killed a lot of the research in traffic science. And so there was development of simulation tools, but there was no new knowledge in those simulation tools. They were implementing existing tools, and there was no calibration even of those particular models, which had seen very little calibration. And so you mentioned early on my amber light stopping problem, where we had, a relatively small number of vehicles, but then we only had 2 parameters, so we could estimate them with a small number of instances. But that was the level of calibration that existed at the time in these models that now are being asked to serve, in simulation models, and on which to base sort of traffic management and so on. So there was a stoppage. And as a result, in the journal, there was less scientific work. And somehow, because as the journal was really very prestigious, the broader OR community wanted to publish vehicle routing, location, etc., area that existed, but then so it became the Journal of Network Assignment, and it was the journal where some of the most significant contribution and static assignment were published. As soon as we went to dynamic assignment, everything was being rejected there, because you did not have provable properties in the same way as static, and so we could not publish really significant papers in transportation science, and we went to other journals for that. So that's always a challenge with journals, but often what you see then, a new journal emerges. So Transportation Research Part C really saved the day for all of us researchers who were working on dynamic problems, which is what we do for ITS.
The reason I asked this was I noticed that Transportation Research Part A was used to be called General.
Correct.
So, and I was going to ask you if you think there is a need for a new journal that be called General.
I still think of Part A as general, frankly.
Okay.
They called it planning and policy to give it a clearer identity, but it still will take that. I don't know that we need more journals. I mean, they established one that they called Interdisciplinary Perspectives in Transportation Research, and I think we've reached a point where it just becomes sort of a money-making thing for the commercial publishers, and I'm not exactly sure. I think you could pretty much place any article in whatever journal there is, and there's a proliferation of other. I mean, if anything, I think we have now the opposite problem. It's just a proliferation of journals with varying standards, with paying, non-paying, and that's kind of changing the entire the entire spectrum.
So I want to ask you about the future, and this is, I don't want, uh, I don't want to ask you to predict because predictions are, we're not in favor of doing predictions on the record. So, but I want to ask you about what are the least developed areas in traffic flow, in your opinion, that might be beneficial for next generation of students to look into.
What about the least developed? I mean, if everybody will see something that maybe we're not thinking about. I do think that we have not studied lane changing and merging maneuvers sufficiently. Largely, data has not been available, but these problems are complex. And they bring out all the complexity of traffic is at these merging points, because that's where the conflicts are. I think understanding conflict and their role is something that only recently I finally kind of got. That what drives all the relations that we see in traffic, the dependence of speed and travel time on density. It's all because of conflicts. And that came out, that realization for me came out in our work with flying objects, with vertical takeoff and landing vehicles, drones, if you want to call it that, which is probably my sort of most recent sort of traffic flow contribution. That's with the dissertation work of Christopher Cummings, where originally I kind of thought we could get a four-dimensional fundamental diagram, which we did, but he was perspicacious and he wanted to get into why is this emerging and what's the mechanism, and he really started looking then at conflicts, which if you do molecular chemistry, I guess you're well aware of. But for us, that recognition was important. And now I could see that conflict avoidance is what drives all of these interactions. And so the conflict avoidance associated with merging maneuvers, lane changing, and so on at these merge points where you have multi-directional changes is where it kind of all comes together. And I think that is the source of a lot of the perturbations that we tend to examine. And so that area, to me, and so that a pure traffic physics is very interesting to me, and kind of the mechanisms that cause that. We understand some of the behavioral mechanisms. I want to try to understand some of the phenomena that are associated with that. And I think that's could be an interesting area to get into. It's not simple. It requires data, because it's not a theoretical question. It's really more of an empirical one, ultimately. That's in vehicular traffic flow. But I think also the whole area of other users, not just automobiles ultimately, but looking at bicycles and active modes in general, micromobility, particularly given the aspiration that people have for how they want their cities to be. There is a huge gap right in there. Part of my prediction is we are looking at potential significant safety problems. And already the numbers that I'm seeing, bicycle fatalities are increasing. They're increasing even in the Netherlands, which is always used as the sort of example of, very high ridership, etc. Their bicycle fatalities are increasing. Interaction between bicycles and everything else, pedestrians, micromobility tools like scooters and so on. I think these are all very important areas of traffic flow that we need to better, to better understand. I think generally we've also, and recently I was pleased to see that Jorge Laval at Georgia Tech, for example, was beginning to examine traffic as a complex system. And that had been the whole mantra of Bob Herman, Ilya Prigozhin, and that's how they came at it. This is a complex system. They had a whole bunch, a lot of work it was bringing together the complexity community and kind of putting traffic in there. That complexity community eventually went in different directions and kind of left traffic behind in a way. And the traffic folks, us, did not quite, I think we had more immediate operational problems that we were working on and did not quite follow or advance the complexity perspective. And I was pleased to see Jorge Laval get back in there, because that's exactly what Bob Herman, for example, was trying to do and sensitize our community to, because again, coming from physics, that's a lot of what they have been doing. So I view those areas as being significant areas for somebody to be looking at in the traffic arena. But there's a lot more. I think, especially as we start seeing more deployment of new technologies, and that's going to be another significant arena. How all of that propagates at network level, again, increases complexity. And I think that's, those are areas. I don't know how much longer I'm gonna, have the privilege to be able to work in this field, but I could easily see the next 20 years of research being taken up with very interesting and challenging problems. We're really not done yet.
You mentioned complex systems and physicists.
Mm-hmm. Yes.
You're talking with Jorge Laval about this. There used to be a lot of physicists doing traffic flow research.
Correct.
I don't know if there are still as many physicists in this area, but I think proportion-wise, they're not. So, and you touched on that a little bit in terms of the nuclear power plants and nuclear research was going away. So a lot of the particle physicists moved to transportation. So, do you see any change in the structure of the researchers, like who is doing this research is impacting the progress of the field?
Yeah, I mean, I think we may have fewer physicists, but we have a lot more computer scientists. That's a different culture. That's coming in. But I have to say that there are still physicists who work on traffic flow. They tend to be more independently minded. They tend not to be in the U.S. So occasionally there would be one or two, then they find their way to the community in the U.S. But mostly physics departments do not hire people who do traffic. I mean, so they're not the academic physicists are not doing traffic flow, and in the U.S. they almost never did. Truth is, it's really in Germany where you've had traffic physics. You have physicists who do traffic, and they have chairs in that. You have people like Dirk Helbing who have entered the field, and others as well. They tend to be in Germany. They tend to be in Japan, where physicists have worked in traffic as a legitimate sort of field for them. And today in China, we see some of them, but I do not know that territory as well. But I do see publications coming out, but I do not know these individuals directly. And they have not really kind of joined sort of the community of researchers. Often what happens is people who are trained in physics who then go into this area. And we see this not only in traffic, we see it in economics, we see it in, there's a lot of, Dan McFadden, Nobel Prize winning economist and econometrician, was trained in physics. A lot of the sort of contributors to econometrics and so on were also trained in physics. So there will continue to be people trained in physics who find their way to traffic flow, but it's not a linear kind of trajectory for physicists. So, and I hope we continue to interact with physicists. They've brought fundamental insights, I think, that are extremely valuable and important. It tends to go sometimes by cultures, by nationality sometimes. For a while, we had people who were trained in Russia, for instance, as physicists who then were kind of entering the field. And so there tends to be waves of that nature as well. But physicists will continue to, I think, to be an important element and contributing group, but it's probably not as significant an originator as had been the case before. We really expect our engineers to have now the grounding in the science and the basic sciences and in traffic physics to kind of advance that and to make their work interesting enough and attractive enough for physicists to eventually collaborate with them.
So if I want to take a step back and look at the last 4 decades that you've done traffic flow research and generally research in general, you've always been ahead of the curve. In many cases, you initiated the field. What was the key? How did you do that? And what was the mindset driving that? I'm asking mainly for younger researchers.
I think you're giving me too much credit, frankly. I've always liked to work in areas that are not very crowded. And I think probably maybe that's the mechanism underlying it. And so, because you can enter a field where there's 1 million contributions already, and your contribution becomes more and more incremental, okay? Or you can find topics where there is not that much, where you kind of have an insight here, and it's easier to start building when there is not too much, frankly. And of course, then it's more rewarding, later on. So partly there's that motivation where you go into area that may not be as crowded, and those tend to be the things that are going to be developing further in the future, of course. And so that's how I like to think of it. And there's always interest in new things. And frankly, I also give credit to my students, who have had interest in areas. And I've always viewed my role as enabling students to pursue kind of their ideas, enabling to pursue their interest. And that means you guide them to sort of find their way and kind of point them in directions where there could be inspiration for their work, because I tend to have a fairly kind of, over the years, enough exposure to different domains and so on. But that's a lot of, when I think of sort of network level fundamental relations, that was partly inspired by Herman and the fact that I had Jim Williams, who was interested in that. I got into the whole crowd business because I had Saad Al-Ghadi, who was interested in that. DTA was a little different because that was, there was a real opportunity there that kind of brought together a lot of my own interests and my interest in, as I mentioned to you earlier, that award that I got from NSF early on is where we started studying user choices. And for that, we were doing experiments that later became known as behavioral economics. That was one of the very first set of experiments. But to do that, we were also using a simulated traffic system to be able to do those interactive experiments to study user choice dynamics. And the models we built, we then used to drive network models where you had multiple routes initially, and that then built into a full, a full network model. So some of it has been more kind of where you could really see the very clear buildup and progression in areas that involve human decisions, traffic interactions, and network structure and system structure. That probably has been, yes, I'm going to say, I can't even say more planned, because at every step was building on something we had, but we saw an opportunity ultimately. And same when we looked at autonomous and connected vehicles, we were kind of building a simulation for a certain purpose. And we then said, but we can introduce autonomous vehicles in this framework. And the rest is history with that. The paper that you and I had done on the influence of autonomous and connected vehicles on throughput and stability. And then more recently, as I've mentioned, the work with Christopher Cummings looking at air mobility, urban air mobility. Yes, I got interested in that working with on a project Uber Elevate before, but Christopher had that passion to look at it as aviation, which is what he was very interested in, and so that kind of got me more engaged in that. Early on, I had a student named Dean Taylor, and he wanted to study bicycle safety. He did the very first dissertation where he was looking at bicycle traffic flow interacting with cars. Still stands out to me. There have not been too many since then. So yes, I've been interested in new areas, but also a lot of it has been through interaction with students and their passion and their interest. He knew more about the bicycling community than I did, and about the experience of the bicyclists. And he then did very rigorous traffic flow research with data that he collected to study these phenomena. And I can talk a lot more about that because that was also an interesting learning experience for him and for me.
Yeah, I would love to hear
So
more
I'll give you an
about it,
example. So Dean Taylor was a very, very strong advocate for bicyclists. And, the kind of advocates that were always, going to City Hall and public meetings and so on. And that was before we had the whole movement for bike lanes. I think he and his groups were instrumental in sort of pushing for more of those. Though Dean was a good bicyclist and did not want bicycle lanes. He wanted wider lanes. Okay, he was more interested in just being able to go with traffic, and that's fine. He didn't have issues. He didn't need the protection, basically, but we needed to understand those interactions. But part of his dissertation was to study bicycles and cars interacting in different contexts, one of which was at stop signs and at traffic lights. When he started collecting the data, he saw all the violations that bicyclists had, and he didn't realize just how unsafe bicyclist behavior was. And so as an advocate, he also felt he needed to advocate to bicyclists to become a little more sort of safety conscious in their behaviors, and that they needed to respect traffic rules as well for everybody's safety. And because when he had video examples of all of that, and that was a very interesting sort of revelation for him.
That's interesting. Since then, there's been some studies, a lot of them from Netherlands, on bicycle safety. So at the time when you were doing that, were there a lot of studies, or just not just here but outside of the US?
You can look at the literature, Larissa. There wasn't nothing. There was very, very little that had studied the traffic flow impacts. In fact, my colleagues in the Netherlands credit me for encouraging them to go and study bicycle traffic, because I several times had made the comments is that if you and this is to my colleagues at TU Delft, is here you are, this top ranked, traffic flow program, and yet you're not doing anything about studying bicycles when you have the perfect environment to do so. So they put together a proposal to the European community, and they got a very nicely funded project to then start collecting data and doing experiments with bicycles. And Serge Hilgendorn will credit me for.
So I wanted to talk about Edie's approach, and so it was introduced for 2D traffic for vehicles, and then later on it was expanded to pedestrians, and also you looked into at the network level to 3D, and you mentioned that for a drone for a 4D.
Yep.
So I'm curious about the relationship when something that elegant and simple can be applied as you even increase the dimensionality of the system. So what does that tell us about the traffic? Does it tell us that there is a simpler underlying dynamics that governs the whole thing, no matter of the dimensionality of the trajectories?
No, it says that the framework is really very general. The definition of these variables is so powerful. It's unifying across the whole spectrum of things that move ultimately. And in fact, I gave at the Herman Award session and at Informs. That's the talk that I gave, was on kind of unifying all these different systems, and it went from ants, all the way through humans to motorized, etc., to birds and drones, etc. So there's a unifying principle that kind of runs through all these systems, and I think we're only beginning to to generalize all of them. And Edie's definition is just so beautiful in its generality. It's just you just have to use it correctly or define it correctly, because we found that when we first applied it to a network, it was not, we had to recognize that the vehicles can only move on the network and not over the entire area. Because for pedestrians, at least for crowds, they could move across the entire area. But even with that, then we had to introduce directional fundamental diagrams and directional speeds, etc. But that can be, done. It's been done now in multiple types of systems. But yeah, defining the variables correctly is an issue. But Edie's definition is so general and generalizable in a sense. In fact, what we're dealing with now is with bicycles, for instance, who may be in a bicycle lane. Are they more like cars, or are they more like pedestrians? And how do you define sort of, these? How do you apply Edie's definition in that context?
Yeah, what really fascinates me about that idea is the equation, even like at a link level, does not, at the same time, does and does not care about if there is a shock wave happening within that area exactly. or not. That's so correct. That is very elegant about it. Yes. So as you expand it to more dimensionality, or
it's an average, basically. It's a way of defining an average.
So I want to connect that to the some of the concepts that you mentioned about Jorge Lavalle, and
yes.
he talks about it. I want to connect that a little bit to that idea, and I want to see what you think about this. So, so in Edie's definition, you look at the area as a factor in it, and you can divide that into smaller areas. And for any one of those smaller areas, this is still applicable.
Correct.
So, and as you can get smaller and smaller, you can capture eventually to get to a point that you see only a few trajectories, very limited numbers. So you can, the average outcome is just representing a single trajectory. So, how does that impact, if you do that, let's say at a breakdown point, how does that impact our understanding of the breakdown formation and the propagation of traffic? So do you think the area that we're averaging or looking at it has an impact on what we get out of the analysis?
And I think in all, yes, in all measures that you define, the specific definition of the spatial and temporal resolution will impact the findings that you have. Absolutely. Some things disappear the more, the bigger your unit of aggregation of, whether it's spatial and temporal. A lot of variability is going to disappear, the more, with that. And so we may, and it depends on then. I mean, that is not so much of an ED's question, but really just in how you define averages when you're looking at macro relations, for example, and that's always going to be the case. I mean, the classic case is when you're looking at at like BPR curves, for example, the old Bureau of Business, Bureau of Public Roads. Volume delay curves. If you have to really increase the observation time to start seeing that particular shape effectively, where you kind of losing the dynamics essentially that exist there. And same will happen when you're looking at phenomena like breakdown and so on. If you want to use these kind of averages for that purpose, you almost have to do it upstream and downstream of where it might be taking place, as well as kind of straddle it. And you want to do sensitivity to both space and time that you use for your aggregation.
So, and
there's no, I don't know that there's a rigid rule there ultimately, but a lot of the art to discovering collective effects, and I learned that from Herman, is how you define the variables. But because only at a certain scale do these collective effects emerge. And the example that I give is that if you wouldn't really have Ohm's law if you were kind of focused on the individual trajectories of the electrons. You would never see Ohm's law ultimately. So it's a question of how far back you step up in averaging and taking your image, your snapshot of the system that that will impact the kind of relation that emerges.
And I know based on what you wrote about Bob Herman, that generally measurement had a special place in his heart.
Exactly.
And so do you think there's room for doing research in terms of how we should measure traffic and what are the...
Totally. Absolutely. Yes. Yeah. And there is research. And in fact, how you apply EDs is important. How you find certain measures from different types of data is very important, and it's not trivial. And in fact, we have had so much incorrect and wrong work being published because of the way vendors produce averages and measures, let's say, from loop detectors. The whole distinction, at a very simple level between, space mean and time mean speed leads to very different results ultimately. And most traffic engineers don't even know that distinction. So there's, there's a lot of, yes, how you define the variable is very important and is definitely a valid subject of research and an important one. The question is then how do you do that research and with what data, etc. But certainly that's very important work. And in case of Herman, it's not just that it's near and dear to his heart. He got really burned because of that. He never got a Nobel Prize because he wasn't measuring at the time, for his prediction. Somebody else did. So that really I think affected his sense of what is important. I
don't have any more questions.
Okay.
Do you think I missed anything in particular? Anything that you think that we should really talk about?
I guess I want to mention something though about professional communities, because one, I think a huge impactful organization for traffic flow has been the Traffic Flow Theory Committee at TRB. And I think I've played a role in this as well in kind of keeping in making it more of an international forum, I would say, because they really still to this day probably one of the best forums or the most effective forums for work in traffic flow theory. That's where you can reach, sort of kind of the most important researchers that you want to reach, both established ones as well as junior ones, up and coming ones. And we kind of take it for granted, but it really was not always that way. But it's one of those that again, some choices that one makes that can be really important for your career, was to go and join or go to meetings of the traffic flow theory committee, which at MIT I did traffic flow work, but there really was nobody who was interacting with the traffic flow theory community. Everybody was interacting with demand, economics, or whatever. And so I went and especially when I first moved to Texas, I submitted papers to that community. In fact, our amber light problem, we also submitted to that committee, but we submitted the network fundamental diagram work there as well, and it's one of the committees that very quickly made me a member because they didn't really have many junior people joining. The chair of that committee was not really a traffic flow person, but more of a traffic engineer. Very nice gentleman who was at UT Arlington at the time. And I was at Texas Austin, and he right away kind of introduced me and kind of adopted me in that committee, which had no international members, none at the time, was presenting work that you could say was a little more capacity than it was traffic flow theory. So it was interacting more with capacity committee, was not receiving very many papers at all, and then was doing some signal type work and some simulations. I had Ed Lieberman, who had developed NetSim, who was there, so there would be an application paper occasionally on that. There would be some arterial coordination, which was more signal control, but Carol Messer was involved in that committee as well. And then after a couple of years, they asked me to be the paper review coordinator. It did have someone from Federal Highway Administration, Paul Ross, who was a physicist, was a researcher, and who knew Bob Herman. What had happened is that the whole traffic science community had split off from TRB because before my time, I think their papers were rejected, and there was kind of a dissonance between the traffic scientists, the GM folks, etc., and the TRB more engineering bent of the DOT, etc., and Federal Highway. And somehow they decided they were never going to go there again. And I had to convince Herman when we submitted our work that let's submit it there. And it was fun. And then they were very receptive of that work. And we sort of rebuilt a pathway into that committee for all the people that you see today from the Netherlands and other places. I invited folks to join that committee. I started using them as reviewers because I was handling paper reviews. And then our sessions more and more became interesting. And that kind of fed on itself, where the committee is what it is today. It's one that receives more paper than any other committee. It has an international chairperson, and and it's really the place not just for the U.S., as a venue for presenting that work, but for the world. And I'm proud of that. Actually, I'm proud that we brought this back to TRB because we needed a venue. We did not have it. We had ISTT once every 3 years. We needed something that was maybe a little less rarefied and selective, but still have, high quality research that was also reaching the agencies, because that's the main, what TRB gave us was a way to reach agencies, because Federal Highway has always had some interest in that arena. And a lot of the ideas for the NGSIM and so on came out of that committee through the federal highway people, particularly from the Turner Fairbanks Saxon Lab, who were present, who were interacting with the researchers, and it takes, it took little effort, but it was very much something I tried to do by inviting these folks to participate. And then I chaired, especially when then I was asked to chair that committee, when I could then appoint international members, and that just developed and grew. So it was also a confluence of time when programs in Europe were looking for where to engage with the community, and then the fact that I got people like Herman's name to be associated with what was being published. I even reached out to Gordon Newell at Berkeley at the time to at least review. And others started coming back to this committee that also developed it. It wasn't single-handed. There was the whole group of Berkeley that then also came along, because neither Gordon Newell or Carlos Daganzo were interested in interacting with TRB at the time, but then their students were, and that kind of brought that line of work into the committee as well. In addition to the other places that were doing traffic flow here, but it just really became the place where you wanted to reach your peers and agencies, etc., more so than the journals.
And I think to this date has kept that spirit.
Exactly.
It's one of the most welcoming communities, if not the most welcoming community at TRB.
Okay.
Yeah, thank you so much, Hani, for taking time. Appreciate it.
Sure,
Really
absolutely.
enjoyed the discussion. Yeah, thank you.
Yeah.